All right, let's just jump right in. We're about to look at an idea that might completely flip your intuition about what makes things in our universe stable. We're going to dig into some incredible research that suggests the most lasting things in the cosmos aren't held together by pure force, but by their actual shape.
So, let me just ask you, what makes something stable? I mean, really, think about it. Your gut instinct probably goes straight to energy. You know, things settling down into their calmest, lowest energy state. But what if that's only half the story? What if the real secret is all about structure, geometry, and, well, knots?
Okay, so here's the classic idea, the one we all learn. A ball rolls to the bottom of a valley. That's its lowest energy state, and yeah, that's stable, makes sense. But now look at the other side, a knot in a rope. It couldn't care less about the bottom of a valley. Its stability comes from its topology, literally, the way it's tied together. You can't just gently push it and make it fall apart. Nope. You have to perform a very specific set of moves to untie it. This is a totally different and frankly much tougher kind of stability.
Now, to even begin talking about knots existing at a universal scale, we have to kind of upgrade our physical language. For the longest time, physics was all about point particles, little dots. But here's the thing. You can't tie a knot with a single point. You need something more, something that has some length or shape to it.
And this is where things get really, really cool. Modern physics doesn't just talk about simple fields anymore. It talks about what are called higher form fields. Let's just walk through this. A traditional field, a zero-form field, interacts with a point. Simple. But a one-form field, that interacts with a line or a loop, like a string. A two-form field interacts with a whole surface, like a sheet or a membrane. And as you go higher, you get fields that interact with entire volumes. All of a sudden, the fundamental stuff of the universe isn't just dots anymore. It's strings and ribbons and sheets, things that can actually twist and braid and get tangled up.
So that brings us right to the heart of the matter, the core idea of this research. The authors call it the coherence structure paradigm. And honestly, it's a huge claim about what's really holding everything together at the most fundamental level.
And here it is. This one sentence is really the key to everything. Physical stability is often associated with topological coherence rather than energetic minimization alone. What that's really saying is that things stick around because their structure is locked in, like a perfectly tied knot, not just because they've gotten lazy and settled into a low-energy state.
So, what does it mean for physics to have these knotted structures? Well, for one, they are incredibly stable configurations. They're really, really hard to unravel. They act like conserved quantities, like a piece of information that the universe goes out of its way to protect. And this isn't just some local effect, it's a kind of organization across the whole system. In fact, this idea is so powerful that it's the foundation for what could be the next generation of computers, topological quantum computing.
Okay, I know what you might be thinking. That's a neat idea, but is it just some weird fluke? Well, this research says absolutely not. In fact, this whole principle, stability through topology, seems to show up again and again. To really see what I mean, we're going to take a quick trip up the dimensional ladder, starting right here in our own reality and going all the way to the wild edges of string theory.
So let's start at home, right here in our familiar 4 dimensions of spacetime. Down here, the theory suggests that stability comes from these things called topological solitons. The easiest way to think of them is like self-reinforcing waves or patterns in a field that just refuse to fall apart, kind of like a smoke ring, but made of pure energy. This is the first step on our ladder of structural stability.
Okay, one step up the ladder. Let's imagine a universe with 5 dimensions. Things immediately get way more interesting. The stable states aren't just simple patterns anymore, they can form these incredibly complex braided spheres and even knotted tubes of energy. With more room to move, the universe can tie much fancier knots.
Let's keep going. Up at 7 dimensions, this whole principle gets even more wild. Entire one-dimensional loops can basically inflate themselves into stable, solid 3-dimensional volumes. Imagine taking a simple rubber band, and it suddenly just pops into a stable, solid ball, all because of its underlying topology.
And finally, let's go all the way to the top, the super abstract realms of string theory, somewhere between 10 and 15 dimensions. Up here, this principle is basically the law of the land. Stability has almost nothing to do with energy. It's all governed by these huge networks of intersecting membranes, or branes, and their arrangements are dictated by these incredibly deep mathematical structures called exceptional symmetries, like E7 and E8. At this level, topology isn't just important, it's everything.
Wow. Okay, that was a pretty abstract journey up through the dimensions. So let's bring it all crashing back down to Earth. Because this theory isn't just some beautiful philosophical idea,
It actually gives us a number, a concrete, measurable tipping point where the nature of a system completely changes.
To find that number, scientists came up with something they call the effective coherence metric. You can just think of it as a structure meter. It's a tool that can analyze a really chaotic system, say the magnetic field swirling around our planet, and it spits out a score. A score from 0, which means total random chaos, to 1, which means perfect lockstep order.
And this is the number that all the research points to, 0.72. And this isn't just some random value. It seems to be a fundamental threshold baked into the physics. When a system's coherence score hits this exact point, its behavior just transforms.
This table really breaks it down for us. So, when that coherence score is below 0.72, the system is just noisy and chaotic. You get little random disturbances here and there, but they're all disconnected. But the very moment that score hits 0.72 or goes above it, bam! The entire system snaps into a globally coordinated state. It's no longer a collection of random parts. It starts acting like one single unified thing.
So, we've got a wild theory about cosmic knots and this critical number, 0.72. What does any of this mean for us, here and now? Well, it turns out it could have massive implications for a very real-world problem, predicting dangerous space weather.
And this is really the bottom line. This 0.72 threshold could be an incredibly powerful early warning system. It could be the key to telling the difference between some minor local magnetic turbulence and a truly dangerous system-wide magnetic storm that's about to get globally organized. And those are the storms that pose the biggest threat to our satellites, our GPS, and even our power grids on the ground. It's a totally new way to see the storm coming, not by looking at its raw power, but by looking at its underlying structure.
So, we end up right back where we started, but with a whole new way of looking at things. The most stable objects in the universe, from those little solitons in our own spacetime all the way up to the fabric of reality and string theory, might owe their very existence not to brute force, but to elegant form. It leaves us with a pretty mind-blowing question to think about. Is reality itself just one big, beautiful cosmic knot?